Today, we will talk about some features. We may have mentioned features. You may remember that the face detector, you may have some special patch. For example, white, black, white, or white, black, white. Those kind of image patch that could detect this part of the face or this part. So if you want to fool the face detector, you could just cover your hair until to here, and it will remove one of the major features from your face. Once again, a feature in a simple sentence, a local feature is an image pattern which different from its immediate neighborhood. So like black, white, and white, or this kind of features. And you can see a figure like this from our left-hand side to the right-hand side. So this is one figure from my own paper in 2015. The paper is about the features for text in the environment. So from the left-hand side, you could see the low-level features. For example, some edges we already mentioned about, for example, canning or Sobel filter, etc. There are also something about like the key points, fast Harris corner, or some feature of blobs, for example, MSER. From our left to right-hand side, sometimes we call it a mid-level features. For example, sometimes we also call from detector to descriptor. Whenever you detect a feature, you need representation to describe it. For example, one of the most famous one is the SIFT descriptor. There are more than 30,000 citations for SIFT. And there are also some other descriptors for different shapes. And from the right-hand side, you will see more and more maybe part of the object. For example, detecting an object, first we want to know where are the features. And second thing is how are we going to use a representation so that it is invariant to different properties. That would be where problem versus a what problem. So essentially the pipeline, you will want to know where is this kind of thing, and the second thing is what. So for example, if you want to detect a face or detect one of the objects, what kind of challenge do we have? For example, it could be like low contrast, right? And under different illuminations, it will become quite difficult even to find the edge, right? Suppose you see a face from different angles. Maybe you could see it from this side or the other side, or see it from the front. So that will also make it challenging. So yeah, let's take a look at those challenges together. This is Viola-Jones face detector. Which one the detector could see on those three examples? If you know something about Viola-Jones, which one the Viola-Jones face detector will still find it? On the left-hand side or the right-hand side, some of the trend features, for example, the white, black, white, so it's not that obvious in other different perspectives. Yeah, so the viewpoint variation become one of the challenge there. We will also mention this later, that if you have a Connect sensor, you have a 3D sensor, then if you could find some of the key points on the face, for example, those 2 points, maybe the mouth or maybe nose, okay? So that you could actually build a 3D mesh, and that could help us to detect faces from different viewpoints. Also, we mentioned about the illumination, part of the edges on the face. It would be pretty hard to detect. Yeah, and the gradient is not that sharp. Let's take another example here. Like occlusion is another challenge for this problem. But it's very interesting that for human, you still can see, oh, this is still a horse, right? And someone is riding it. Yeah, so actually our human perceptual system is quite good at recovering those kind of things. The other would be, for example, scale or deformation. So you could see that there are a few horses in this picture. Their shape are not that uniform, right? But our perceptual system could still recognize that we have a few horses in this picture. Or even more challenging is that suppose we are saying a chair, and there are several different types of the chairs. So the intra-class variation become another challenge. Finally, some kind of noise, maybe from the background, and it will kind of ruin the object detector, right? So this is also something in nature, some animals will behind some cluttered background so that it could fool the visual system of the predator. And we have seen challenges 1 to 7 so far. Ideally, we could develop some local features. Those features are unique to others, and they are invariant to some of the challenges, some of the transformations. Yeah, for example, if you see a truck on the left-hand side, and if you see it from different viewpoints, the features may rotate somehow, right? And ideally, your feature could be geometric invariant to those translation and rotation, or even better, the scale. Ideally, just like another challenge about the illumination, so if your feature could be invariant to brightness or some like exposure, then that will help our robotic vision system to find the same feature again. Okay, and today we will just introduce some of the features for today. They are like my favorite feature detectors or descriptors. And you could find much more in the VLFeed library, or you could also find them in OpenCV. So today we will start with the fast corners, and then we will talk about the shift, one of the most widely used features. Finally, we will mention about the brief. So the first one, I like this feature detector. The reason is that it is very fast, so that it's feasible for many of the robotic applications compared to other features. So the full name is features from accelerated segment. Let's take a look at how the algorithm try to find the corners. So we start with a center C. Okay, center pixels, and we find a radius of 3 pixels. So you could see it would be something like maybe something like a clock. Okay, and around those radius r equal to 3, these are circles. There are 16 pixels. Okay, and the testing started to find the longest run of pixels whose intensity is either greater than the C plus a threshold or less than that of C minus the same threshold. So you could imagine that suppose you have a black pixel in the center, okay, and you start to loop those 16 pixels. For example, the pixel at the, the 12 o'clock direction is within threshold plus or minus, then we will set a count. From the description, it might be just too confusing. So let's take a look at the figure. Here, the C is more like a white pixel over here. So here is a pixel center C over here. Or sometimes we also call it a nucleus or something. We started from here, 1, 2, 3, 4, 5, 6, 7, etc. Okay, and we try to find the longest round. of this. So if we encode those testing as one string, just by zeros and ones, what will this look like? So this is the C, and we try to find the test intensity value, right? And we want it to be within a threshold. Suppose within the threshold, we call it 0. For example, this one is like a black one, and we just set it to 1. So we will have more like a string composed of zeros and ones. For example, 0, maybe 0, and then 1, 1, 1, 1, 1, 1, etc., and then back to 0, 0, 0. Right? So essentially, we want to find the longest run of probably just the ones, so that we will see this is one of the corner here. So this is a basic principle of the fast corner. Okay, so let's take a look at the algorithm again. We want to find at least 12 consecutive ones. So we have 16 in total and 12 out of 16, so that it will become a corner like this. So this is probably one of the pretty simple ways to find a corner. Here comes a discussion. Suppose on our embedded system, we like it. We found 12 consecutive ones, and we found that this is a brilliant idea to find a corner. Can we make it even faster? Okay, so there are 3 questions here. And the second question is like, why radius of 3? Longer or shorter? Okay, and the last question, what kind of corner will you get, for example, in this picture? Is there any way to make it even faster? You could think of that now I have a center, I found the intensity value, right? I need to do the testing for 16 times in order to find, okay, now I got 12 ones. I think the C is a corner. Is there any way to make it faster? So maybe compared to those 16 times testing. Sampling, you just check, maybe suppose it's a clock. You just check 12, 3, 6, and 9. So there was a paper in 2006 that's called FAST feature. And later on, they published another paper by this idea. Yeah, that's good. So that you reduce the number of testing by just 4 testing. Do you guys agree this method? Suppose you sample just 12 o'clock, 3, 6, and 9 o'clock. You would quickly reject non-corners. The other way to make it faster could be, for example, if you find 0 and you have consecutive 12 ones, right? And then you don't need to check on the rest. You just break. You can pretty sure that it's a corner already. Or you need to find 0, 1, 1, 1, 1, 1, 1, and 0. And you could make sure that it's a corner. So you could have, for example, some like early break to determine, quickly reject non-corners. Or you could try to set up, and then do you guys learn about like regular expression? Suppose you have 0, 1, star, and 0, right? And the ones is greater than something. Then you could have a faster computation. All right, how about radius? Why 3 pixels, longer or shorter? Let's take a look at this picture again. The radius look like this, right? 3 pixels. Suppose you have a radius of longer, maybe 5 or 7, maybe 9. And do you think it's a good way, or what's the pros and cons to find these corners? If you have longer or shorter radius. How about the next question? Now our setting is 12 out of 16 pixels, right? So what kind of corner will you get? 现在可能有一些，假设一个 fast corner run 在这个图上面，那哪些地方 fast algorithm will think which part is a corner in this example? 的端点这个吗？ 还有没有？这里有没有？这里有没有？有哦，好。Okay, how about here? How about here or maybe here? Now our setting is 12 out of 16, right? Maybe how about those guys? Maybe here. How about here? No? Why not? We have more like a conclusion that maybe some kind of terminal. Here, here, and here. Our first fast detector could find it, right? Because it's very easy to get 12 consecutive ones. How about those guys? Maybe here or here? How about that? Try to run a fast detector maybe by OpenCV. So actually, depending on what's the setting there, right? So suppose it's 12 out of 16. You could imagine that any angle that's maybe smaller than 90 degrees, the fast algorithm could find it. Then if it's slightly bigger than 90 degrees, then it's probably not. There are also some principle here. Now I would like to challenge you a little bit more. So this is one of my own paper in 2015. We would like to find different types of corners. Just like we said, there might be some terminal style corners. There might be some V-shape, L-shape corners, or maybe some feature like curve, right? Or a T-shape, Y-shape, X. So is there any way maybe use a similar principle as fast detector to find different kind of corners here? Suppose we want to find different shape like T or Y or X. What kind of principle we could apply something like fast detector in order to find maybe V shape or maybe L shape or Y or X? 那有没有就是例如说 X shape 或是 T shape？ 我们刚刚在做一个 encoding， 对不对？我们刚刚有做一个，例如说 0, 0, ones and 0. Then what will the X or Y shape looks like in those kind of encoding? If you are interested, please read the paper. So the basic principle is that we do exactly the same thing like the fast detector, and we do the testing. In real world case, you will need to do it for a few different radius. Otherwise, you will miss something. Okay, so there are some detail in the paper. We would like to talk about the SIFT, the scale invariant feature transform. So this is one of the most famous paper or one of the most influential paper before deep learning came out. Yeah, and you could see the more than 34,000 citations. So this is one of the classic paper. This is Professor David Low, so please remember this guy. Yeah, he's a giant in computer vision. And essentially, there are a few stages. First, scale space extrema detection. Second, key point localization. And third, orientation assignment. And finally, the key point descriptor. And today we will focus a little bit about the descriptor. So this is one of the pre-processing of the SIFT. So in the beginning, it actually also compute the gradient. Okay, and then try to remove the low contrast and the edges. And this is the way the SIFT uses a representation to describe point and its neighbor. The basic idea, take a 16 by 16 square window around the detected feature. It's like something like the shape we just saw. You can consider that, okay, this is maybe around a V-shape location. And then you try to find its surroundings. So now over here, it's a 16 by 16. You compute the edge orientation for each pixel. Throw out weak edges. If you remember, for example, the Sobel filter, we always compute a gradient with magnitude and the orientation, right? And then here, according to the magnitude, you could just throw out some of the stuff you don't want, some of the locations you don't want. Okay, and finally, you create a histogram of surviving edge orientation. So you could see on our left-hand side, yeah, suppose there is a center point somewhere around here, and try to compute 16 by 16, and you could see an arrow represent the magnitude and the orientation of the gradient, right? And then you try to turn it into a histogram like this. So according to the orientation, you will have from 0 to 2 pi. Okay, and the orientation, it just quantize it to only 8 directions. And then from 16 to 16 window, the algorithm further encodes this image gradient into a descriptor like this. You could think that those 4 by 4 windows, if we sum it up, we will have a histogram like this. And those are the orientations, and the length of the arrow is a magnitude. So that in each cell, we will have how many values? We will have 8 orientations, and each one we have a magnitude. This is the basic idea of the SIFT descriptor. Here comes another discussion. We have a 4 by 4 grid of cells. So any pros and cons from here. First question is that how much memory the SIFT descriptor will use for one key point. How do you think? Let's go back here. For example, this one. So here is a key point descriptor. So what's the memory requirement for this descriptor? Now we have a key point descriptor. This is the SIFT, right? Descriptor. What's the memory requirement to build such descriptor? This is like the gradient, orientation, and magnitude, right? So how are you going to save each of this? And then in total, how many memories, like what's the memory, how many bytes? Yeah. What kind of histogram we will need here? So what do you think? Will you use 1 byte, or maybe use a float number to save this? 8个方向，然后你有4个 cell， 8 是32，对不对？ The SIFT descriptor has 16 cells, so now we only see 4 of them. Okay, so here is the memory requirement. It's a 128 dimension vector, and if you use a floating point, so it will take 512 bytes. This is just for one key point. So if you tag a SIFT in a natural image, especially with some clutter image, you will usually get maybe 2,000 to 3,000. So that would be a lot. In fact, for SIFT detector and descriptor, this method, although it's one of the best feature detector, it's kind of expensive in the computation as well as the memory. Okay, because in the beginning, the first step is to compute a gradient. There are also some implementation using CUDA, using the GPU acceleration. This actually motivates us for different kind of descriptor. Okay, here is another descriptor. It's called BRIEF. It's an acronym of binary, robust, independent element features. And then the good thing is that it only 32 bytes per point. That would be maybe 1/100 of magnitude for the memory requirement. So here is how it works. Okay, so first, try to smooth the input image by a 9x9 Gaussian filter. So this is something similar to the tag, right? And then we choose 256 pairs of points within a 35 by 35 pixel area following a Gaussian distribution with sigma equal to 7. Essentially, you want to find some pairs in this 35 by 35 patch according to the Gaussian distribution. Okay, center the result mask on a corner C. Here comes some kind of testing again. If the intensity at the first point is greater than at the second one, add a 0 to the bit stream, otherwise add a 1. So this is kind of similar to a fast detector. And finally, we will get a bit stream, zeros and ones, of length 256. It will become the descriptor for the C. Here comes the, so for example, in this patch A, for the fast algorithm, we did it something like this, right? And now we did it in a quite different way. So we just pick 256 pairs of 2 points, and then try to compare 2 of them and see if the intensity value is maybe within something, and add a 1 or 0 to the final descriptor. Okay, and you may think that this is kind of a random thing, right? So maybe we could see there are some other choice pairs of points. So you could see we have G1, 2, 3, 4, or 5. Surprisingly, some kind of randomness over here, essentially generated by Gaussian distribution from 1 to maybe 1 to 4. It actually give a pretty good accuracy for the descriptor. And for the last one, this one is actually somewhat similar to the fast algorithm, right? Because you can see it try to compare here or maybe here. So a few pairs in these patterns. So this one is more like the fast detector. But some others, they are kind of random, but actually give us pretty good results. And the next step is that for each descriptor, you want it to be, for example, rotation invariant, so that when you, for example, you see something like this in your image, and when you turn it, you will still find the same point. So that's a rotation invariant. So for the matching step, if you have 2 bit strings, we also mentioned this before, we could use the Hamming distance. So we already mentioned this in the AppleTag, right? The decoding stage of the AppleTag. So far, I just introduced some of the detector and descriptor to you. Okay, there are lots more. And in fact, before deep learning came out, feature engineering was the mainstream of the computer vision community. But later on, since maybe 2009 or 10, people start to use deep learning, try to learn the features from data. Okay, so that changed the direction of the community quite significantly. Nowadays, people still want to know what kind of features that will bring us good results. So previously, for example, briefed, you design something, you generate a descriptor for it. But now it's the other way around. It's not about feature engineering anymore. If you have the data, then you use the data to learn what kind of filters, what kind of patterns, what kind of descriptors you could see, okay, from the deep network. Okay, and surprisingly, for example, this is a typical deep convolution neural network, and people try to visualize them. And surprisingly, the early stage of the learned filters looks like what we used to design by hand. That's actually quite surprising. Later on, you could see like different kind of textures came out in the middle, and then some object parts at the later stage. And then finally, the object class. Actually, I think visualizing the features are also important. Because for myself, I have studied those features for a long time. And then suddenly, there comes a new method, and it could learn the feature just by feeding data. That's kind of totally different ways. Right. We just mentioned a few features in 2D. Also interesting to take a look at some features in 3D. So I won't be able to cover too many of them for today. We could play with some features in 3D. But you know, the basic idea is quite similar. So some geometric features, or maybe you calculate the gradients in 3D, and you use a histogram to represent it, just like what we did. And there are already some implementation of 3D features in PCL. I'm sure that the tutorial will be a very exciting one. And the other good thing about features between 2D and 3D is that it could be also used, for example, virtual reality and lots of robotic applications. First of all, we will need to know the transformations. Essentially, we need to know what's a pulse, what's the translation and the rotation of a pulse in 3D. And we already introduced 2D to 3D transformation, which is camera calibration in our OCW. One important step in the lens following is that you want to detect the 2D segments, and then you have a projection, you have a homography to find the segments in 3D space. This is very important so that you could drive your Dockybot correctly in the lens. Some discussion, if you have done that, that's great. If you haven't seen the OCW, please ask yourself those questions. How to do camera rectification, and how to do ground projection. So this is another step. You place Dockybot in front of a checkerboard, and you already know the corners in the checkerboard in 3D, and you see those checkerboard from your camera in 2D. And according to those 2D and 3D correspondence, you could calculate the homography edge. Later on, whenever you detect a line segment, you will be able to find the 3D coordinates of the line segments. Okay, so here comes a question. What if you have a drone or a wearable camera? Can we still do this ground projection? So the question is that for the Dockybot, you have a fixed camera mount, right? So essentially the ground is flat, and you have a camera mount facing just a little bit down, right? And here is the question, what if you have a drone or a wearable camera? Can you still estimate the ground projection just with a pre-calculated edge? I will introduce a little bit more for those. I have done something like this before, and I'm very excited to share. This is some concept you will have to know, the pulse and transformations. Essentially, if you borrow me your right hand like this, for example, this is the pulse of your robot, and you will have X, Y, and Z, right? This is actually the X axis, the Y, and the Z. Okay, so this is one of the popular way to represent X, Y, Z, but in some coordinates, it may switch a little bit, but this is probably the most common way to represent the X, Y, and Z. And in addition to the X, Y, Z and the translations, so this movement, we call it translation. And we also have the rotations. So if you rotate your pulse by this, what's this called? It's roll, right? It's like rolling, roll. And what about this? Pitch, good. And how about this? Yaw. Okay, so this is, if you take a look at those OCW, it's only 5 minutes. Okay, and then you could actually represent a rotation in several ways. So one is roll, pitch, and yaw. So you have 3 degrees of freedom. And you could also represent it by Contanian or 3x3 rotation matrix. And this is also one thing you would definitely want to know. What's the properties of the transformation matrix? So if you learn about forward kinematics, you could do some composition of those transformations, right? And here comes another question: how to calculate the pulse of a detected April tag? So suppose you put an April tag. Let's take a look at this. Suppose you have an April tag and you see it from your camera, and you want to know the relative pulse of an April tag. Then what information do you need to know? We have the code in the repo, the April tag RAS, right? And we actually use it a lot in the Ducky-Tang. So anyone, like how to get what information you have to know in order to know the pulse of a detected April tag. The camera pulse, we usually assume it is just like 000 for translation and just a rotation. There's no rotation. That's a typical setup. Yeah, what else do we need to know? It would be focal fx, fy, principal point cx, cy, right? Okay, great. It's April tag size, because you will need to find from the camera, it's a pinhole camera, right? So if you know the physical size of the April tag, you will be able to know the pulse. Otherwise, it could be anywhere along the array. Right? So suppose you have an application in virtual reality, and you are allowed to place the April tags everywhere in the experiment room. Then you could get a pulse easily. Or some crazy idea, if you have an underwater robot, and you place the April tag everywhere inside the swimming pool, and you could localize the underwater robot in 3D. That's exciting, right? So we know the size of the April tag, we know the camera parameters, and in fact, if you dig into the code April tag, it will tell you that it will use a function called solve PMP. This is a problem, perspective, and point. So this is a problem to estimate the pulse of a calibrated camera given a set of 3D points in the world and the corresponding 2D projection. In the April tag case, you already found the 4 corners in the image. You also know a physical position somewhere in the world because you know the size, so that you could compute correspondence. And this is a very classic problem called the PMP. Okay, and this is how solve PMP looks like in OpenCV. And you can see object points. Those points are the 3D points. And you also see the image points. Those are the 2D points detected in your image. And the camera metrics and the distortion coefficients. Yeah, so if you have a fisheye camera, this is needed. And you got some outputs, rotation and translation vector. And behind solve PMP, so in the class, we usually refer you to use a function. Behind PMP, there are several implementations in OpenCV. And one of the most way is it's called CV iterative. And it used an optimization called Lec05 marker. Theoretical background, we won't be able to cover it too much in the class, but I would like to make another announcement or advertisement that we would like to offer another class called Sensing and Intelligent System next semester. So it will be a graduate level class, and we will introduce more something about AI, like the search or about some optimizations. In fact, LM optimization has been widely used in many robotic research. So for example, the loop closure is called ISAM or some other technique. I think in the beginning we mentioned that your robot just go and then take a loop and come back to the same location. And if your robot is able to detect the same landmark, it could do a drift correction with loop closure. And in fact, the ISAM behind loop closure is also LM optimization. So we will talk a little bit more about some theoretical background in the class. So because we need to make some significant differentiation between this class and next class. But feel free to get yourself familiar with the LM optimization. So essentially, help us to find a pulse that minimize the reprojection errors. Okay, so it's an over-determinate system. For here, again, it's the similar problem. We want to estimate the correspondence of the camera and the ground. It's probably totally fine. You place lots of Apple tag in your own room, and you could check your virtual reality head mount everywhere, easily. Sometimes we want to separate the features into artificial features and nature features. And for artificial ones, because it's very robust, it could actually bring us lots of applications. But on the other side, sometimes we call it a trivial computer vision, which is a solved problem. So that you cannot just use Apple tag itself and work on some application and publish that, because it's like too well established. But if you could find another interesting problem and use this tool to solve it, then that would be interesting. And for nature features, it's still active because it's still very challenging. And reliability is relatively low. And our task would be identify special parts of the physical world, which is the feature we mentioned in the previous section. And we want to find the correspondence between those features in the world and the features in the image. So let me show you another application that takes advantage of the PMP thing. So this is my own paper. It's accepted in the ICRA conference. That's actually the major conference in the field. The problem is that you have a wearable RGBD camera, and you want to find the workable space all the time. Okay, let me show you this. It's more like a pyramid. Okay, you can see it's going like up and down, right? And you can see also the area. So it's become a challenge in that it's not like camera mount on the ducky butt. When a wearable camera when a user is walking, there will be lots of pitch, or maybe some rotations, but usually the pitch. You want to find the walkable, the ground. It sounds like a pretty simple problem, right? But because of the moving camera, it becomes relatively challenging. It's not like a Kinect mounting on a bookshelf. It's a fixed camera, right? But if a moving camera, then you will have to calculate correspondence between your camera and the world all the time. Okay, so in this work, let me show you the algorithm. Well, this is also not a breakthrough, like people can do it. But if you use it in a right application, it will become valuable. Okay, so the input, it's a point cloud from your RGBD camera. And first of all, you estimate the surface normal. And you find the ground plane, G, from the Stixel world. Stixel world is an assumption that indoor environment is either horizontal or vertical. It's more like a Manhattan world assumption. Okay, and the Stixel world, it also try to build something, it's a bar. And then one important thing is you want to rotate all the points in the point cloud according to normal and the ground height. Finally, for example, if you want to find a chair, one easy way to describe a chair would be like the chair, you have a horizontal surface about knee high. Assumption is that you have your point cloud perfectly aligned on the ground. Okay. Otherwise, you won't be able to know, oh, it's a knee high, right? Or even it's not flat, it's not horizontal surface. This is another video. Try to detect some chairs. Okay. Okay. Okay, so far, actually in indoor environment, it's relatively easy. But the challenging is that suppose you want to do it outdoor. It becomes quite challenging. So for example, this is the data collected in Boston. So you could see this is the Freedom Trail. It's become a pretty hard problem because the ground is not that flat. The outdoor, there might be some illumination and some occlusion. It's not that easy to compute a good surface compared to the indoor. Outdoor is much more challenging. So this is one of the examples to estimate the ground. Estimate the ground is actually very useful, for example, for wearable device. And it could also detect the drop, or also maybe some other object, for example, chairs and table, right? As long as you know the ground. And the other interesting application is to estimate the head pulse. Okay. So we mentioned that earlier in our lectures that if you could find some 3D points, for example, you have an RGBD camera, and you find some, for example, the nose, the eyes, skin, yeah, and then you have 2D and 3D. And you could calculate relative pulse for it. So here is one of the interesting head pulse estimation. Okay. Yeah, and then you could try to cover some of the feature points and see what's the minimum points you will have for the PMP, right? Okay, the other application is to estimate the gas pulse. Okay, so it's more like checking your eyes. And it could be also an interesting application. For example, if someone with ALS, 渐冻人, the eye become probably the only thing he could move by himself. There are also some other applications. For example, the Facebook acquired Oculus before, right? And then now it acquired eye tracking company called iTribe. You could imagine that eye tracking is also an important aspect for virtual reality. Okay, and it's also used the same technique. So for your eyes, calibration and validation. So the typical case is that on the screen, the program shows 9 dots at the corners, okay, 8 in the center. Okay, and they ask the users to move their eyes to see all the corners and then do it twice so that they could calculate the drift. Okay, so that's the basic principle. Okay, so this is something probably similar to previous one, the head pose estimation, but a little bit different way because previously there is a RGBD camera, but here you have a calibration and validation step. But the basic principle is similar.